Hi, everybody. We're going to do one more review thing. This is an optional quiz I give to my classes. They have now finished with it, so I'm sharing it with everybody else. This is going to be some common Regents concepts. So these are things that I know to be on the Regents pretty much every year. Some of them I can pretty much guarantee are going to be there word for word. Other ones are just ideas that are typically on the Regents somewhere, and we're going to see how we do with all these. I've got, it looks like 40 minutes till I need to be in a meeting, and an alarm that's going to go off in 25. So let's hope we can get to these 23, I believe, this questions pretty quickly. First one, if a decimal is present, read the number from left to right. Present equals Pacific, and if a decimal is absent, read the number from right to left. Absent equals Atlantic. So this is about significant figures. We want to name how many significant figures are in each number. So again, if a decimal is there, we're going to say it's present, and we'll read from the Pacific side from left to right. If a decimal is not there, we say it's absent. We read from the Atlantic side. P for Pacific and present, A for absent and Atlantic. We ignore any number that's not or we ignore any number that is a zero until we find a non-zero digit, and then we count that and everything after that. So in the first number, I see no decimal; it's absent. We read from the Atlantic side, from the left, from the right. I see a 0 and a 0. I ignore them. And now I finally see a non-zero digit. That's the 5, and that's the one that's important. So one sig fig here. If there were any numbers before the 5, they would also count. In this one, the decimal is present, so we read from the Pacific side, from the left. And the first number I see is a 5. So as soon as I see something that's not a 0, that is important. We count that and anything after it. So the 5, the 0, and the other 0 are all significant 3 sig figs. So the difference in these very similar numbers are going to be just whether or not there's a decimal there, 1 sig fig, and 3 sig figs. For this one now, it's still pretty close. Decimal's present, read from the left. The 5 counts, so it and anything after it count. So 1, 2, 3, 4, 5. All these digits are significant. That's going to be 5. After this one, now the decimal is absent. We read from the right side, and I ignore all these zeros that I see first until I see that 5 at the end, and that's going to be just 1 sig fig. And as I'm doing these, I can see in my answer key that they're marked incorrectly on the assignment my kids all did, so I'm going to have to go through and regrade all my students. So whatever, I'll get to that eventually. This one, decimal present, read from the Pacific side, ignore all these zeros we see first, until I finally see a non-zero. That's the 5, so that's only 1 sig fig in this one. And on the last one here, again, decimal present, so I read from the left. I ignore all these zeros. The 5 I see, now I count that and anything after it, and that's going to be 2 sig figs. So there we go. Next one, a measurement of the atomic radius of platinum atoms was made to be 143 picometers. Based on table S, what is the percent error of this measured value? So talking about percent error, we're going to have a formula for that. I'm going to go to the back page of my reference table and find the formula for percent error. It is the third from the top, and it says the formula for percent error is going to be percent error equals the measured value minus the accepted value. So whatever you measured or estimate or guess or anything, minus the accepted value, something we know to be true, divided by that same accepted value, and then times 100. So some number times minus another one equals, divide by another one, equals, times 100, it equals. So I'm going to write right here, measured minus accepted, over accepted, times 100. We're going to plug some numbers in. It says a measurement was made to be 143 picometers, and based on table S, what is the real number? We're going to find the percent error. So it says measurement is made is this. That's our measurement. 143 is going to be our measurement. I'm just going to block that off. We need to go to table S and find what the actual number is. So I'm going to find the atomic radius of, let's say, platinum. Platinum. So I'm going to find the element platinum. Atomic radius is all the way on the right side here. I'm going to look for platinum. Let's see where platinum is. Platinum should be on page 2, I believe. And where's platinum? Right there. Platinum is number 78 on our chart. So I'm going to read all the way to the right-hand column. And we're going to see what the atomic radius of platinum is. So that number is going to be 130 picometers. So that is our accepted value. So 143 was our measured. 130 is our accepted. Divide by that same 130. And then don't forget to multiply by 100. I'm going to plug that into my calculator. And it's going to be 143 minus 130. I'm going to hit equals. Divide that by 130. Hit equals times 100. And it says my answer is 10% error. My answer, the error of the person was 10% off. So that is choice A right here, and there we go. Question 3. Which substance can be broken down by chemical means? A very common question. Can be broken down by chemical means you can break it down into something simpler. It's not just changing state. You're not just melting or boiling or freezing. You're changing into other things, into other parts. If you look at this question and don't have a clue what it's asking you, just take a look at these choices. I see carbon, I see CaCl2, I see cobalt, and I see californium. Does any one of them look very different from the others? Well, this one sure looks a lot bigger than the others. These are single element, single element, single element. This is two different elements with actually three atoms combined. That's going to be the difference here. Can be broken down by chemical means you can break it down into its parts, much like you'd split up water into maybe H's and O's. That's what this is asking for. CaCl2 can be broken down into its separate Ca and Cl parts. That's going to be the difference here. If you saw a question that says which one cannot be broken down by chemical means, it's asking you to find the element. And this one can be broken down by chemical means it's going to be something that's not an element. This is multiple elements. That could still be split up into its parts. These guys are all as simple as they can be. Graphite and diamond are two forms of solid carbon and STP. These forms have what? I know I've seen this question a couple times in videos I've done the last few days. Graphite and diamond, those are two really, really different things. Think of what a diamond looks like. Think of what graphite, the quote-unquote pencil lead that you write with, looks like. Those are two totally different things. They have totally different properties, and they're going to have totally different properties because they have totally different structures. So let's say different structures and different properties. That's going to be your answer. If you think of these two things look nothing alike, they act nothing like each other, they're going to have different properties. You can cross off anything that says same properties and then say, well, why do they have different properties? It's because they're very different from each other, different structures. Under which set of conditions will a sample of a real gas be expected to behave most like an ideal gas? I give 4 giant red arrows pointing to this question in class every year. This is something you gotta know. To behave most like an ideal gas, how we expect gases to behave, this kind of theoretical idea of how gases should act. We want gases to have lots of energy, be basically bouncing all over the place, spreading out as much as they can, not being held back, not slowing down. To do that, you want something with high temperature, so I'm gonna get rid of the low temperature choices. And you want something with low pressure. You're not trying to hold it into a container, you're not trying to squeeze it somewhere you want to fit into. You're just letting it go wherever it wants to go. So no to high pressure, yes to low pressure. The only choice that's going to make sense, is B right here. High temperature and low pressure. High temperature, lots of energy, going wherever it wants to go. Low pressure, you're not trying to confine it anywhere. Again, allowing it to spread out and go where it wants to go. We can measure gas samples in terms of their pressure, temperature, volume, and number of molecules. If different samples of gas have 3 of those 4 values in common, then the fourth also will be equal. That was Avogadro's hypothesis. At STP, which sample has the same number of molecules as 2 liters of CH4? If you have any number of gas samples, could be 2 samples, could be 10 samples, whatever. If you have pressure, temperature, volume, and number of molecules, moles of gas you're looking for, not moles of gas, molecules of gas, if any 3 of those are the same, the fourth one also has to be the same. So if you know any 3 things, whatever it may be, are exactly the same as between the 2 samples, the fourth one between them also will be the same. And this one, it says at STP. STP means standard temperature and pressure. That means these 2 samples of gas have the same temperature and pressure. So if we're looking for temperature, pressure, volume, and molecules, we now know temperature and pressure are the same. It says which one has the same number of molecules. So we're looking for this one to be the same. If these 3 are going to be the same, we're going to accomplish that by having volume also be the same. So we have to have the same volume between 2 samples of gas. It says 2 liters of CH4. That's the volume of one of the gases. That means the other gas also has to have the same exact volume. Just look for which one has the same volume. And right here, it's 2 liters of oxygen gas. Question 7. An atom of nitrogen-16 contains how many protons, how many electrons, how many neutrons? Protons determine the element. Nitrogen's always going to have the same number of protons, no matter how many nitrogen atoms you have, no matter what the nitrogen type is, what isotope it is. Nitrogen will always have a set number of protons. Its atomic number 7, it's going to have 7 protons. Get rid of anything that does not say 7 protons. Now we're down to 7 protons, but how many electrons, how many neutrons? It says atom of nitrogen. That means it's neutral. That means the charges are balanced out. Protons will be balanced by electrons. So there should be the same number of electrons. So you're looking for 7 electrons right here. So this one's not going to be correct. Anything that didn't say electrons, I mean, we've already crossed these choices out, but you could eliminate it that way. And in terms of the number here, 16, that's telling you how heavy the thing is. That's the mass of this version of nitrogen. That's like if you had N with a 16 written up top as its mass. 7 will be the atomic number at the bottom. 16 tells you protons and neutrons combined. 7 tells you how many protons. So the neutrons are just subtracting these numbers. 16 is protons and neutrons. Of those 16, 7 of them are protons. So subtract, and the other 9 are neutrons. So 9 neutrons are what you're looking for. Choice A, for all those reasons, is the only one that makes sense. Not 14 neutrons, not 14 neutrons, not 7 neutrons. This is the only one that makes sense. Compared to the energy of an electron in the second shell of an atom, the energy of an electron in the blank. Third shell is the same, first shell is higher, first shell is the same, third shell is higher. So that's when you're talking about your rings. Here's your nucleus right there. Here's your first shell. Here's your second shell. And there's your third shell right there. Electrons in the first ring right around the nucleus have some amount of energy. The electrons in the second ring have even more energy. I'm not drawing nearly enough, but that's okay. And electrons in the third ring, the third shell, have even more energy than them. You get more and more energy the farther out you go from the nucleus. There's more space to fill. It's more bigger pathway to move around in. You get more energy the farther out you go. That's how excited states work. So compared to electrons in the second shell of an atom, does the third shell have the same amount of energy? It does not. It's going to have more. Does the first shell have higher energy? It does not. Does the first shell have the same energy as the second shell? It does not. Do electrons in the third shell have higher energy than the second shell? Yes. That's how it's going to work. It's framed in terms of comparing it to the second shell, and the third shell does have more energy in its electrons than in the second shell. An element's bright line should be an element, not a element. An element's bright line spectrum is produced when excited electrons do what? So that was this. Because we know electrons have higher energy the farther out you go, when an electron gains energy, so some energy came in, let's say, and hit this electron right there and excited it, it would jump out to the farther out ring. It could be here, it could be another one. That's the excited state. It's normally in the ground state where it normally is found. If an electron gains more energy, it can jump up to a higher ring with that extra energy. Now, to go back where it came from, it releases that energy out again as light. So it's when an electron drops back where it came from, drops and returns to a lower energy level, that's where it releases the energy. So this bright line spectrum is the pattern we see. It's like a kind of a light barcode. It might look something like this. And every element has its own pattern. That's when an electron drops back down again. It releases energy. So we're going to cross off anything that says absorb energy. And it drops to a lower energy level. So it's not going to a higher energy level, not going to a higher energy level, all the way left to zero. Releases energy as they move to a lower energy level. Absorb energy and go to a higher ring, release energy right back and go back to a lower energy level. Which electron configuration represents electrons of an atom of neon in an excited state? Same idea, these last three questions. Excited state is where you gain extra energy and jump to a new ring. You're not gaining and losing electrons, you're not getting a charge. It's just your electrons are moving out of order, they're kind of cutting in line and going somewhere where they're not typically found. This tells us it's going to be neon in an excited state. So we need to have the correct number of electrons for neon. We can look that up on the periodic table. And then it's just got to be out of order, not what the periodic table tells us as the typical electron configuration. So let's see what the table actually says. For neon, it's element number 10 right there. Try to avoid the shadow from the camera. And it says atomic number 10. So it'll typically have 10 electrons to balance out these 10 protons. And we know how they're arranged because it says 2-8 as the electron configuration. It usually has 2 electrons in the first ring, 8 electrons in the second ring. So this is what neon normally looks like, 2-8. 2 electrons in the first shell, 8 electrons in the second shell. That would be the ground state. Well, I see that choice right here. So that's definitely not going to be an excited state because that's what the ground state looks like. I'm going to cross it off. We need to have these same 10 electrons. So any choice here that doesn't have 10 electrons, we can get rid of. 2 and 7, that's only 9 electrons. That's not enough. That's not going to be our answer. 2, 8, 1. 2 plus 8 is 10, plus 1 is 11. That's too many electrons. That's not going to be our answer. Right there we have our answer. Let's just see if it makes sense. 2 and 7 is 9, plus 1 is 10. That's the correct number of electrons, as choice B had before we cross it off. But we know from the periodic table this is what it normally looks like. That's the ground state. We want to be in an excited state. So at least one of these electrons has to have jumped to a higher ring. Instead of having 2 in the first ring, 8 in the second ring, it looks like one of those 8 jumped up to a new level, and that's why we have 2-7-1. It still got 10 electrons, but one of the 8 now formed a third ring, and that's our choice. That's going to be an excited state for neon. Based on table S, An atom of which element has the strongest attraction for electrons in a chemical bond? Hopefully by now you've done enough questions. Maybe you remember from earlier in the year, you've seen some old Regencies, but you look at this question and see the phrase strongest attraction for electrons, and really even just the words attraction for electrons, and say that's electronegativity. That's just a definition vocab word to know. Electronegativity is an atom's attraction for electrons. So the strongest attraction for electrons means you just have to go to table S in the periodic table on the reference table and find what the electronegativity is. So I'm just going to go right here. It's table S, and it's got a whole column for electronegativity. I'm going to look and find this stuff. Aluminum says its electronegativity is 1.6. Magnesium says it's 1.3. And as I'm going through this, you remember that nonmetals want electrons more and metals don't. Metals should have smaller electronegativities. That may help you kind of zero in on a choice. Sulfur is going to have an electronegativity of 2.6. So again, I'm seeing my metals with much lower numbers. And chlorine has an electronegativity of 3.2. I'm looking for the strongest one, the highest number. Chlorine is going to be my obvious choice. Nonmetals have higher electronegativities, metals have lower ones. You don't have to remember that, but you can look it up if you have to. Which statement describes the energy and bonding changes as two atoms of fluorine become a molecule of fluorine? Two atoms of fluorine become a molecule of fluorine. So we'd have something like this. We'd have two Fs, and they're going to go together and form something like that, F2. Something in that kind of way. So in each choice here, we see either energy is absorbed or energy is released, and either a bond is broken or a bond is formed. Well, if I have two different atoms coming together to make one molecule, as the question tells me, that's going to be a bond forming. So I'm going to get rid of anything that says a bond is broken. Right there, I knocked two choices off the board. And then you just have to remember, well, is energy released or absorbed when bonds are formed? I always think it's easier to remember it the other way. If I want to break apart this molecule that already pre-exists, I need to put energy into it. Bonds are stable. Bonds are happy. Molecules are good. If you want to break that molecule apart, you need to use energy. You have to zap it. You have to give it electricity, give it heat. You have to put energy into that bond to split these things apart and reverse this process. That being the case, the opposite would also be true. That when things come together, they release energy. Think of it, these atoms right here are just kind of flying around by themselves. They have high energy. When they go together and lock together, they have to calm down. They have to get to a more stable place. They have to lose energy to do this. So energy is going to be released, like everything instead of absorbed, as a bond is formed. The bond between which two atoms is most polar? Polar means asymmetrical. Remember SNAP. Symmetrical means nonpolar, asymmetrical means polar. So if it's talking about which is most polar, it's saying which of these four choices is the most unbalanced, the most uneven. It always goes back to electronegativity. So I just need to go to that same electronegativity list I had before and find the electronegativity of all these different elements. I'm going to start at the beginning. It says H, and that's going to be 2.2. And I see oxygen is not too far down the list. That's 3.4. Difference between those two numbers is 1.2. I just subtract. For N and H, well, I just saw H is 2.2. I see N on my list is 3.0. Difference between them is 0.8. So it says which one is most polar, means the biggest difference. Of these first two choices that I did, this is a bigger difference than this, so C is not going to be our correct answer. For C and O, I know that O is O is 3.4. I looked it up a second ago. For carbon, it says 2.6. So that's going to be a difference of 0.8 also. So that's now still lower than 1.2. We're going to get rid of that one. And for F, these are both the exact same number. F has an electronegativity of 4.0. It's the highest electronegativity, but they're the same number. So the difference is absolutely nothing. They're both pulling with the same strength on the electrons. This is going to be my most polar bond here. The biggest difference in how strongly each side is pulling on the electrons is in this one. 1.2 is the difference. The others have a smaller difference. Question 14. What is the chemical formula for sodium oxalate? Anytime you're looking at this, if you have to try to figure out what a formula is, look at what you're dealing with. The metal names don't change. So if it says sodium, sodium is a metal, it's telling you exactly what you're starting with. This is going to be one of my starting materials, Na. For oxalate, look at how the name ends. If it ends in an IDE, so if it was something like oxide, something like that, the IDE ending tells you just change a non-metal's name to have an IDE ending. This does not end in IDH, so this is not going to be a non-metal element, which means oxalate has to be some kind of ion. So I'm going to go to my polyatomic ion chart. I'm going to look up what oxalate looks like. Polyatomic ions are on table E, and let's see if we find oxalate, and there it is right here. C2O4 with a -2 charge. C2O4 with a -2 charge. That's oxalate. We still need to know the charge of Na, so I go to my periodic table, and when sodium is forming a charge, it's going to be a +1 charge. All right, now I know these two ions are going to go together to form some kind of compound. And we have these options right here. So I want to just put them together. I'm going to say Na with C2O4, and now we have to figure out how many of each one. This one here, we're going to do our crisscross. We're going to bring that number down to tell us how many of C2O4. Because it's only one, I could write a 1 here with some parentheses, but I don't need it. Just leave that as C2O4. The 2 over here, we're going to bring that down to tell us how many of the NAs we need. I'm going to write that number right there. So we need 2 NAs to balance one of the C2O4 ion. So let's find something in the molecule here, in the choices. It says Na2, C2O4. And there it is right there. You may be tempted to try to reduce this because you see 2 and 2 and 4, but you can't take those numbers out because C2O4 is actually an ion. So you have to keep those numbers exactly as is. So you're really looking at 2 and 1. We don't write there, but it's 1. Could you reduce that? And you can't. That's your choice. Na2, C2O4. You could have eliminated this once you know it's not just oxygen, eliminate that once you know it's not just oxygen, and we still would have been guessing between A and D, but D is the right one. I'm going to take 1 second to turn off the alarm on my phone because that's about to go off. So let me just pause this real quick. Okay, and we will have plenty of time to finish the last 5, 6 questions, whatever this is. There's not that many on here, although I think the last page is kind of long, so maybe I'll have to pause anyway. All right, sample of water is used to dissolve 100 grams of table salt and NaCl. Compared to the properties of pure water solvent, the solution of salt water will have either a lower or higher boiling point and a lower or higher freezing point for each choice here. All right, when you have pure water, we know pure water, if we had a temperature scale, is going to boil at 100 degrees Celsius and freeze at 0 degrees Celsius. That's pure water. If you get it as a liquid, you heat that liquid up to 100 degrees, it's going to boil into a gas. If you cool that liquid down to 0 degrees, it's going to freeze into a solid. Once you add anything to it, anything that's going to dissolve any kind of electrolyte or non-electrolyte, but especially the electrolytes that break them up pieces, it's going to change the properties and become more like a mixture of those things. It's not just water, so it's going to lean a little bit in the direction of the stuff you mix into it. So this is not just pure water anymore. It's going to start to act a little bit more like the salt you dissolved into it. So it's going to go a little bit of a higher boiling point. Boiling point will go up, and freezing point will go the other direction and start to go down. So at this point, if you have the salt water, maybe you have to heat up to 101 or 102 degrees. Maybe you need to cool it down to -1 or -2 degrees to boil and freeze respectively. So it's always going to move away from the center. The boiling point is going to go up, freezing point is going to go down. So I'm going to get rid of anything that says lower boiling point. I'm going to get rid of anything that says higher freezing point. And that's going to eliminate a couple of choices. And we're going to left with higher boiling point, lower freezing point. It's called boiling point elevation, freezing point depression. Systems in nature tend to undergo changes towards what? Either higher or lower disorder and higher or lower energy. Guaranteeing you this is going to be on your test. I will guess which question this will actually be in a couple of days, but it's always going to be energy spreading out, energy going down. Sometimes you see the word enthalpy for this. Sometimes you see energy, but it's going to be lower energy you look for. So I'm going to cross off higher energy. Things do not suddenly get hotter on their own. Things get colder. Heat spreads out from the sun. Heat spreads out from an oven or a heater or a hot plate of food. It's going to go down as the energy spreads away. You also have an increase in disorder because pieces start to break down. It's a lot more likely that a mountain starts to get weathered and crumbled or a statue starts to erode than suddenly pieces build themselves back up again into more orderly things. So you look for higher disorder, so I get rid of lower disorder, and you look for lower energy. So I eliminated 3 choices. What I'm left with right here, higher disorder, that's entropy. So you look for high entropy. And lower energy, that's enthalpy. You look for low enthalpy. That's your combination. A reversible chemical reaction has reached equilibrium when? What does it mean when something's at equilibrium? You have something like A going to B, and B can also turn back into A. At equilibrium, the rates of these reactions, the speed with which A turns into B, is going to be the exact same speed at which B turns back into A. So you have some of A turning into B, some of the B turning into A, and it's not just one each. You have maybe a million A's, a million B's, whatever. You got plenty of these things. So there's always some of the A, there's always some of the B. You don't have the same amounts of them, but whatever they are don't change because the speeds are the same. They're going to be constant or equal speeds of the forward and reverse reaction. So if we look at our choices here, it looks like they all say something about the rates and the amounts. Rate of the forward reaction is greater than the rate of the reverse reaction. That is not true. We want the rates to be equal. Rate of the reverse reaction is greater. No, rates of the forward and reverse reactions are equal. That looks pretty good. Rates of the forward and reverse reactions are constant. Rate does not need to be constant. It just needs to be equal. The speeds are equal to each other. And the amounts of reactants and products are constant. Yes, the amount of A and the amount of B stay constant. They don't have to be equal to each other. You could have much more A than B or much more B than A. It doesn't really matter. But you don't see any change in the amounts because as soon as some of the A turns into B, an equal amount of the B turns back into A and everything stays exactly where it is. The amounts don't have to be equal to each other. They just have to be constant. The rates have to be equal and the amounts are constant of their own. There you go. Compare the A solution, I guess it's supposed to be compared to a solution with pH 3. A solution with pH 5 is a hydronium ion concentration, which is what? So we're comparing things on the pH scale. You have your low numbers down here. Those are the acids. And then the higher numbers are the bases. This is only asking about things with pHs 3 and 5, so I'm just going to draw the beginning of the pH scale. These are your stronger acids all the way on the left, bases be in the other direction all the way on the right. And it gets weaker as you go towards the middle, towards neutral pH 7. So compared to something with a pH of 3, so compared to something right here, something with a pH of 5 has what? Hydronium ion is H3O plus. That's the ion that forms when the H given off by acid jumps onto water. H2O becomes H3O plus. So this ion right here essentially tells you how strong an acid something is. So the lower pH with the really strong acid identity is going to have a much higher concentration of H3O than things farther over to the right when you really become a much weaker acid, neutral, and then eventually a base. Remember on the pH scale though, every time you move one pH unit, it's a tenfold change. So something at pH 3 is going to be a stronger acid by 2 pH steps. The question is asking us to compare to pH 3 and say how pH 5 is. So pH 5 is going to be 2 spots to the right. So it's going to be a weaker acid. It's going to have less of this H3O ion. So anything that says greater, we're going to get rid of. It is not greater concentration. The ion concentration is going to be weaker because we're moving in the non-acid direction. Well, how much weaker? It is 2 steps on the pH scale. This is a 10 and then another 10 fold change. So 10 times and 10 times, it's not adding them up. It's 10 times 10 equals 100 times weaker of an acid. It's only 2 steps, but if every time you move, it's a tenfold change. So if, let's say it was pH 1 to 5, it would be 10 times 10 times 10 times 10. You'd have a bigger number. If it's only 4 to 5, it's only 10 times. This is 10 times 10 is 100 times, and it's weaker because you're going towards the right, away from all the acids. Right, let's look at the last, or maybe 1 or 2 more real questions. We got some fill in the blanks. According to one acid-base theory, as soon as I see that phrase, one acid-base theory, that is Bronsted and Lowry that we're referring to in the question. Those are the 2 guys that did not agree completely with Arrhenius. Arrhenius said that acids give off this H plus and bases release OH minus in solution. That's when the H and OH go together and form water. Bronsted and Lowry are 2 people who did not totally agree with Arrhenius. They said, yeah, you're somewhat right. We're kind of with you in some ways, but other things we disagree. They defined bases as what? They agreed with Arrhenius that acids release H plus. They just called it donating a proton, H plus being the proton, but they said acids are proton donors, and they said nothing about the OH. So if you see the OH, that's entirely Arrhenius. Bronsted and Lowry referred to bases as things that do the opposite. They don't donate a proton, they accept a proton. They accept H plus, they accept a proton. So they said nothing about OH. So we're going to cross off anything with hydroxide. That's entirely Arrhenius' theory. Bronstein and Lowry, this one acid-base theory talks only about H plus. If it's, the question says H minus, get rid of that. That's not sensible. It's not OH minus. It's only H plus. So proton donors are the acids, proton acceptors are your bases. All right, for table M now, we've got a bunch of pH indicator questions. Gives a little example or a little detail up here about how to actually use this. I'm just going to turn to table M because it's much easier than reading this. The written stuff was, if kids got questions wrong in my class, they could go back and get an explanation of why it was wrong. But here's table M. This shows a list of indicators. It shows the color change that happens, and it shows the pH range over which that change happens. So for methyl orange, the color change will take place between pH 3.1 and pH 4.4. At any pH below 3.1, so 0 all the way up to 3.0, the color will be red. Between 3.1 and 4.4, that's where it'll start to go from red to yellow. So you'll see different shades of oranges in that range. And then by the time it gets to 4.4, it will have turned yellow. And if you test anything with a pH 4.4 and above, so all the way up to 14, it will look yellow when you put this indicator chemical methyl orange into it. So using that info, let's fill this in. Litmus will appear what color in a solution with pH of 11? So let's see litmus, and we want to see pH 11. So let's check the color range. pH 11 is going to be higher than pH 8.3, so it'll be on this side, and litmus would look blue. Next one, methyl orange will appear what color in a solution with a pH of 3.3? We just looked at methyl orange. It said, 3.8. So in this color range, 3.8 would fall right inside here. So that's going to be going from red to yellow. So it's going to be some kind of orangey color. So it's more on the reddish end, so it'll probably be more of a reddish orange, but I'm just going to write orange. Brom crystal green will appear how in a solution with pH 1.7? Brom crystal green, and we want 1.7. Here's Brom crystal green. pH 1.7 is below 3.8, so it's going to still look yellow. Bromthiamyl blue at 6.8. Bromthiamyl blue right here, 6.8, again, is going to be in this range, so it's going to be going from yellow to blue, so it's going to be some kind of green, some shade of green, I should say. And phenolphthalein with a pH of 5, phenolphthalein, pH 5 is definitely below 8, so it's still going to appear colorless. This is if you're doing a titration and you added the acid first, almost real colorless. It's going to be clear. Once you get it to a basic range, that's when it actually turns that nice kind of pinkish color. These are the choices, not the answer, so don't get confused by those. All right, last little bit here. Redox reactions. Redox reactions involve the movement of one or more electrons from one element to another. We have those couple of things to remember. Leo says Gur. We know that the loss of electrons is oxidation. The gain of electrons is reduction, but it involves the movement of electrons. When an element gains electrons, gaining electrons, its charge goes what? If an electron is negatively charged, then gaining electrons means your charge is going to go down. It's going to get more negative. This process is reduction. Gaining electrons is reduction. In a voltaic cell, battery, this process takes place at one electrode. We know it's reduction, and the other thing to remember is the red cat sitting on an ox. Reduction happens at the electrode known as the cathode. Oxidation happens at the electrode known as the anode. So if it's reduction, that's going to be at the cathode electrode. When an element loses electrons, it loses negatives. Its charge goes up, becomes more positive, and this process is called oxidation. In a voltaic cell, a battery, that's what the song, this process takes place at an electrode called what? Where does oxidation happen? Oxidation at the anode. We start at the anode. Electrons are lost there. I'm not going to sing the whole song. Go Google or look on YouTube for the anode song. When looking at table J, metals that are higher up are more likely to undergo what? Metals want to undergo oxidation. Metals want to lose electrons. That's why they typically form positive ions. But when you have two metals reacting, they can't both be oxidized. Someone's going to have to take on electrons. So to see who wins, we see which one is the most active metal. We just compare where our metals are on here, and the higher up the metal is, the more likely it's going to be oxidized. So the higher up metal will undergo oxidation, and the other metal will, at least in that example, that instance, be reduced. And nonmetals conversely, that are higher up will undergo reduction. Usually don't see the nonmetals. There's only 4 of them on here, but the higher a nonmetal is, the more likely it's going to be reduced. If you're comparing 2 metals that react with each other, the one listed will undergo oxidation, as I said a second ago, and take the role of the anode. Oxidation happens at the anode, so if you're higher up on table J, you're going to be oxidized. You are the anode, and that's where the process is going to start in the voltaic cell. Which formula represents an organic compound as a member of the alkyne homologous series? All the organic stuff, and then we go to table Q, and we see that alkynes have a triple bond, they have the name ending in YNA, and they should have this general formula, CnH2n minus 2. However many carbons they have, the number N, they will have twice the number 2n minus 2 number of H's. So we have to see which of these choices has CnH2n minus 2. Start with your carbons. If it's got 3 carbons, it should have twice that number is 6, minus 2 is 4 H's. C3H2, not enough H's. If we have 6 carbons, you should have twice that number is 12, minus 2, it would be 10 H's. Too many H's. If you have 4 carbons, you would have twice that number is 8, minus 2 is 6 hydrogens. This looks like it's going to be correct. Let's just double check the last one. If you have 5 carbons, you would have 2 times that number would be 10. Minus 2 should only be 8 hydrogens. This one says 12. Not going to make sense. There we go. That's the one that follows the ratio for our alkynes. One question left, and that's perfect because I have a meeting in 4 minutes. Let's say, which of the following equations represents a spontaneous nuclear decay? Spontaneous nuclear decay means that one of these things on table N, these radioisotopes that are already unstable, these things are radioactive, they're going to break down their own, and they're going to do it by giving off one of these particles here. Either fancy looking A alpha, fancy looking B minus, that's beta, fancy looking B plus, that's positron. One of these particles will be released, and then they'll turn into some other type of element. So you want to look for one element on the left of the arrow, and on the right side of the arrow, one of these things, either alpha, beta, or positron. Sometimes you'll see some gamma radiation also, and turning into some other element. So, looking right here, I see lithium and H being combined seemingly and then breaking apart. That is not a spontaneous reaction. That is 2 things being put together. It's not going to happen. Aluminum and helium, same thing. That is 2 things being combined. That's not going to happen. Right here, uranium with a neutron, and then it seems like it's breaking apart. That would be what nuclear fission looks like. This is the only one that looks like what it should look like. We've got radon, one element on the left, giving off an alpha particle to turn into polonium. If you just go and look for one element on the left side, turning into something else, so this is the only one of our 4 choices that look like that. The other 3 choices all have more than one thing, more than one reactant on the left of the arrow. It's the only one that starts with one reactant because it's spontaneously breaking down. It does not need any help from anybody. It doesn't need to be hit by a neutron, hit with a alpha particle, hit with a proton. This is the one that's going to be spontaneous. That is choice A. Perfect timing. I've got 3 minutes to spare. Hopefully this helps a little bit. These are really common issues, really common topics, I should say, that almost guaranteed will be on your test. Good luck.